we talked a little bit about level flight performance the last time we talked. That was before we flew, and so that's been some time ago. And we're looking at a propeller-driven airplane, so we're going to talk about the methods for a propeller-driven airplane. There are a number of different approaches you can take. You could go up and fly at each altitude at various power settings and record the airspeed. I know some folks years ago at Piper who did that. It's terribly inefficient, you know, to determine level flight performance that way. There's much better ways to do it, and we're going to talk about one of them here today. But that's, you know, that's a possibility, and I've known folks that did it. One we're going to use here today we call PIW, VIW, or sometimes you'll see it as PEW, VEW. Essentially what that means, the PIW is a normalized power, VIW is a normalized airspeed. And you're going to see those kinds of terms pretty much through the rest of the course, because this method is fairly simple and straightforward and gives you good data at a kind of a minimum expenditure of flying time. The nature of this business is that you, although we love to fly, that we do as little as possible, okay? Because it costs money. It's not so much money in a GA airplane, but you start talking bigger airplanes, and all of a sudden the cost, you know, runs into literally thousands of dollars an hour. So, you know, we try to minimize the amount of flight tests that we do, and this is this method does that. Power required can be determined from this equation. You know, here's the true airspeed cubed. Probably all reasonably familiar with this equation. Remember, this is power. So what happens, we multiply power as thrust times the velocity. And so we end up with our drag term, or power term, having for, you know, a cubed function. Remember, that was a squared term when we were just talking about drag or thrust, right? That was a squared term. And so was this one here. But when we multiply through by power, which is thrust times velocity, we've got, okay, that turns that into a cube term, and that into 1 over velocity. Okay, and we said last time we talked that what did that do to everything that we generally think about? You know, like I said last time, in universities these days we've forgotten about reciprocating engines and propeller-driven airplanes. We've just forgotten about them because, we've got jets and we're going to talk about jets. They're more cool, you know. Trouble is, we've had propeller-driven airplanes, and I think we'll have propeller-driven airplanes through all of our lifetimes. Because a propeller-driven airplane in certain cases is more efficient than a jet. You can never make a jet engine quite as efficient as that reciprocating engine that's in our Cherokee 6. You know, we try and we run the temperatures up, you know, get them up about the temperature of the sun, and we might get close, but they would probably melt. So anyway, so here's this equation of the thrust horsepower required for a level flight. But we're not going to leave it there because it's got too many variables. You know, we've got true airspeed, so we've got to figure out what the density is and all that sort of stuff. And as I've said earlier, us flight test guys are sort of simple-minded, and we don't like to, you know, we don't have a very good memory, so we don't remember all those tables of density versus altitude and that sort of stuff. But I do remember density at sea level, 0.00237 slugs per foot cubed. Now, I'm still in the English system, all right, the old English system. You know, we invented the airplane, by the way. All right? So, you know. So anyway, so I can't remember all of these things, so we're going to try to simplify a little bit by saying things I can't remember. We can achieve that if we assume that a given angle of attack, both CL, lift coefficient, and drag coefficient are constant at a given angle of attack. That's a pretty good assumption for a given airplane, okay? But particularly below Mach 0.5, which is the kind of airplane we're dealing with here in this course, you start getting up to the transonic regime, things begin to change, and that assumption begins to kind of break down. But below that, you know, the drag curve is pretty constant and what have you. So we can equate sea level standard day conditions to non-standard conditions, you know, test conditions, and that's what we want to do. So if we say in level flight at small angles, we generally say that the lift is equal to weight. You know, we have sines and cosines. We generally say, oh, those are small, and we kind of ignore them. You know, we make sure the math's right, and then we ignore it. But anyway, if we do that, we combine the previous assumption, we can say that test weight, 2 times the test weight over density times this is the actual density, times the 2 airspeed squared times the wing area is equal to 2 times the standard weight of the airplane, okay, times the sea level density, times a term we'll call VIW, and again wing area. And if we solve that equation for the VIW term, we have equivalent or calibrated airspeed for the test value. That's what the T stands for, okay, that's the test value, divided by the weight ratio, test weight over standard weight. So in case of the Cherokee 6, 3,400 pounds is the standard weight, we'll call it, okay. So whatever our test weight was, that's why we want to know what our weight was at our data point. And that's all times the square root of that weight ratio. So a fairly simple equation for this VIW term. And then if we solve this thrust horsepower, we'll call it thrust horsepower IW, and before long we're just going to call it power IW or PIW. Okay. But anyway, we put those each over each other and we do some cancellations and we come up with this term. And then we can say that thrust horsepower IW, or the standard sea level value, is equal to test value times VIW over true airspeed cubed, and 1 over the test value of density ratio, sigma. And then we can take that one a little bit farther and we substitute in here for VIW, and we come up with this equation. Thrust horsepower, the test value, times the square root of the test sigma, the weight ratio over essentially 3/2 power. Now we have 2 values of a given data point. and we're gonna call that thing PIW, which is the test brake horsepower actually times the square root of the density ratio divided by the 3/2 power of the weight ratio. Okay, and then we go back, PIW then becomes a function of VIW, or vice versa. Now, let me see my eraser here. And we're going to plot that up. Again, down here, we're going to plot VIW and PIW on this axis. And what we're going to do is we're going to get a bunch of data points. That looks like a curve that you've probably seen before. This is really the power required curve. Out here on this end is the max level flight speed. That's as fast as you can go in level flight. And this, by the way, is a sea level curve. It's what the airplane would do at sea level. But you can use that curve and those equations in reverse to take it to any altitude you want. So you end up building this curve, this VIW curve. Once you have that built, you can do that in one flight. Once you have that curve built, then you can publish all kinds of data. You may have seen some handbooks that will have a set of curves that look something like this. Where this is altitude, and this is true airspeed. And sometimes you will see placed next to it a density altitude chart with, you go in with temperature and altitude, you come up and you come across here, and that gives you the density altitude. You read across here, say, well, this beam, let's say this is 75% power, and this is 65%, and 55%, and this curve here, like I say, I don't draw very good, but this is a full throttle, and maximum RPM. Okay, so this is the best the airplane is going to do with everything forward in level flight, and this is what's going to happen at various power settings. Okay, and then with this over here, now you have all of the, the pilot can go in and say, okay, my outside air temperature is at 7,000 feet, let's say, is such and such a degree, and we go up here and read this chart, this being the 7,000 foot line, we come across, and I want to fly at 65% power. Well, here's how fast you're going to go at that altitude, okay? So you can use that for flight planning and all those kinds of things. Now, when you get up there in today's world, we have GPS. Back when I started doing this, GPS wasn't around. In fact, we hadn't even thought of it back in the 60s, okay? Nobody even thought of GPS. Number one, we hadn't put up that many satellites. We were still in the business of thinking about satellites. Today, you don't hardly need that stuff because the GPS gives you what your ground speed is, because the purpose in having this kind of a chart is to find out how fast you're going at altitude, and then take the winds at the altitude and the component of the winds and see what your ground speed's going to be. Today we have ground speed right on this little magic box. It's in the instrument panel. Okay? So it's almost made a lot of this stuff go. However, everybody likes to advertise that my airplane's faster than yours. Okay? So we still do this, and we still need this data. And it also tells us, using this kind of thing, we can come up with stuff like drag. So we can use that in our calculations for the next airplane. You know, where is the drag in this airplane? And how do we get it out? When I worked at Piper, many years ago now, I always thought that, the Cherokee 6 and the one we had was a 1966 model. I worked at Piper in the 70s. And I always thought that those wheel pants just didn't look right. You know, I always called them the old bird feather wheel pants. You know, it looked like the next time you're at the airplane, take a look at the wheel fairings and the struts, you know, on the landing gear. They look like a chicken. Okay, you know, those feathers don't go all the way down to his feet, you know, so they kind of look like, and if you really look at it, man, there's all sorts of, you know, there's brake lines and there's all sorts of stuff there that isn't really good aerodynamic shape, okay? So I got to thinking about that, and my bosses were away. They were in Europe for extended stay, like 6 weeks. And so I decided, being left in charge of our group, I decided that I would work on reducing the drag on the wheel fairings. And we did. We gained those versus, if you've seen my airplane, some of you have seen my airplane, I've got the new, what were the fairings that wheel fairings we developed. There was 5 knots in each of the main landing gear, primarily due to interference drag. And we got all of it out. Those new fairings, and you'll see them on some of these Piper airplanes, although Piper charges way too much for them. But you'll see them on new Piper airplanes. They have no separation on them at all.
At all? How do you keep it color?
You don't. One of the things, a mistake that everybody makes on wheel fairings, they do a double teardrop shape. You can do this one, but you can't do this one.
Spray the Cessnas when they come back to
You know, you got to keep the top flat, and particularly where the intersection between the strut and the fairing is, that has to be a 90-degree angle. That was what we discovered in doing this. We, in the process, during this 6 weeks, we made 5 different configurations before we got to that. Okay. And we tufted each one, go up and find, take pictures, and come back and try to get rid of some of, and the only way we could get rid of all of the separation was keep the top of that fairing horizontal and do it this way. And if you'll look at those fairings, they're much bigger. You know, the airfoil is about a 20% thick airfoil that's on the new wheel fairings, which is much thicker than the ones that's on the Cherokee current Cherokee 6 that we fly. But each main fairing has 5 knots
And you design
less
for,
drag.
you design for cruise speed, right?
Yes, yeah. However, they help them climb too, because, you know, we just reduce the drag. In fact, during that time, we had a fixed gear Cherokee 6, which Piper never marketed, because it was within 1 mile per hour of the retractable. A fixed gear airplane, okay? Within 1 mile an hour of the retractable. And of course, they didn't want to sell that, they wouldn't sell any retractables. But that's the kind of drag that's available in these airplanes. And I think there's probably another 10 knots you can find there fairly easily, in addition to that. And I tried to get them to do it. At that time, gas was still pretty cheap, 50 cents a gallon versus, you know, I think I paid,
$10 now.
I think I paid $3.30 yesterday, and that's, I consider that cheap these days, okay, you know, for my airplane. So anyway, so here's what, you know, here's this thing, you know, we'll go out and we'll do 2 altitudes just to show you that this stuff all collapses into a single curve. But you can, if you do it at low altitude, you can get the whole curve. You know, if you do it at about 1,000 feet or go out here at 500 feet over the ocean, you can get this whole curve in one flight. Like I say, we'll do 2 altitudes just so you can see. Now, we won't be able to, you know, if we go up, say, 7,000 feet, we won't be able to get this far of the curve, because we won't have the power up there. But with that, we can get all of the level flight performance for the airplane. Well, how do we do this? Here's for a constant speed propeller. Now, I'll tell you, for a fixed pitch propeller, there is one more term that you've got to use, you know. Here, we only end up with one curve, PIW, VIW, and our data points. What you have to do for a fixed pitch propeller, you go PIW, NIW, and you get a curve that kind of looks the same, it's a little sharper. And then you have to have 2, you have to have NIW, which is propeller RPM normalized, times VIW. And there you end up getting, and you can, with this one, you can develop a palette chart for the engine. And this one, of course, you know, the 2 of them, you can eventually get to this point for a fixed pitch propeller. In this case, fixed pitch propellers are more complicated than our controllable propellers like we have on the Cherokee 6. Okay, so how do you go about doing this? Well, we go out and we do level flight performance, and, you know, we get stabilized on a point. We try to do the high speed points first, because it takes a while for an airplane to stabilize. I used to hate to fly with magazine writers. You know, the guys who write for Flying and those kinds of magazines. Because they get in the airplane, you know, they get in the airplane and climb up to some altitude and level off and immediately read the airspeed indicator. Oh, well, your airplane's slower than you say it is. You've got to let the thing stabilize, stupid. You know, I mean, but they would consistently do that. I hated to fly with them because I would guarantee that was what was going to happen. It takes a while for the thing to stabilize. 5 minutes probably to stabilize at the maximum level flight speed, with everything pushed forward. Okay, so you get up there and you level off at your test altitude and you know, got everything forward and you sit there and you wait. The other thing is this requires that you do a good job of holding altitude. Okay, so, you know, you're sitting here for 5 minutes. This performance for a test pilot is the hardest thing to do, rather than stability control. Test pilots like to do stability control. They don't like to do performance. And the reason is that performance flying is both boring and precise. Think about that. How many of us as humans like to do boring things but do it real precisely? We don't. Okay, so here you are, you're sitting there waiting for this thing to stabilize. Of course, it's accelerating, so you have to continually retrim it to its hold altitude. But still yet, you're just sitting there waiting. Okay, finally it gets up stabilized, and we say read, and you read what that data is, and now what are you going to read first? What's the most important parameter? Here's the other secret to hand recording, okay? You record the most important